Chapter 15, Number 62. Tests of lung capacity show that adults are able to exhale 1.5 liters of air through their mouths in as little as 1 second. A. If a person blows air at this rate through a drinking straw with a diameter of 0.60 centimeters, what is the speed of air in the straw? So we're going to essentially use a dimensional analysis, and we're going to say that the volume that passes through the end of the straw in some amount of time. So if we sort of say, here's the end of the straw, and we say we start our clock and we blow through for 1 second, so we get some volume of air in here, and that volume has to be, well, the area of the cross-section. So the volume would be the area of the cross-section of the tube times this distance, because we've basically taken this thing and smeared it out over the 1 second. And so this, what we might call the distance S. But then we can say that distance is clearly v times t. Right? The speed that the air is moving times the time it moves for. Dimensionally, if you look at that, we have meters squared times meters per second times seconds, which becomes meters cubed, and it is in fact a volume, which means I can turn this around and say that the velocity is the volume of air, so that's pretty bad volume of air over the area times time. So we have 1.5 liters over the area is going to be pi r squared. The diameter is 0.60, so the radius is 0.30 centimeters, quantity squared, and the time is 1.0 seconds. Then we're going to use that 1 liter is 1,000 cubic centimeters. That's a conversion factor you can find online or from chapter 1. And then down here we're going to have pi times 0.3 squared, which is 0.09, and we'll have centimeters squared. So 5305.2 centimeters. We'll want it in meters, so we'll divide by 100. And then we might as well recognize that we only have 2 sig figs, so we end up with something like 53 meters per second, which is pretty fast, but there you go. Part B reads, if the air from the straw in part A is directed horizontally across the upper end of a second straw that is vertical, as shown in the figure, to what height would the water rise in the vertical straw? So here we're going to have to play some games about what we're talking about. So let's call this pressure right here at the bottom level, well, that's going to be 1 atmosphere because the whole thing is open to the atmosphere and nothing's going on. And of course, likewise, the pressure here is going to be lower than 1 atmosphere, and we know we'll be able to say that pressure, call that P1, plus 1/2 rho air times velocity squared has to equal 1 atmosphere. In other words, by blowing through the straw like this, we lower the pressure at the end point compared to the general atmosphere because the air is moving. But we also know that the difference here, that P at the bottom of a column of water minus P at the top of the column of water has to equal rho of the water times GH. And combining these two things, right, we have that this tells us that P atmosphere minus P1 is 1/2 rho air V squared. And so down here we have that 1/2 rho air V squared equals rho water GH. We're solving for H, so we'll divide everybody over, and that will give us a new equation where we'll have rho of air over rho of water times V squared over 2G. The rho of air is 1.29 kilogram per meter cubed, and the rho of water is 1,000 kilograms per meter cubed. Those both come from table 15.1 from your book. And then we just found 53 meters per second as our velocity, so we do that with a square, and we've known g for such a long time. We end up with 0.1847 meters, which we should certainly round to the correct number of sig figs, which is 0.18 meters, or about 20 centimeters, which is significant.